So, two types of friction we're going to talk about is kinetic and static. Kinetic friction acts in opposition to an object's motion once it's already in motion. Okay? You can write down an abbreviated definition of that. You're not going to have to know the definition of that, but you do need to know that kinetic friction is friction of an object that's in motion already. Okay, the size or the magnitude of kinetic friction depends on the two surfaces that are interacting. Okay, that's what makes a difference for our size of frictional force. The two surfaces that are interacting. So if you've got ice on ice, do we think our frictional force is a very big amount? No, but if I've got carpet on carpet, probably a pretty big frictional force. Okay, so there's a value that will help us determine what the size of our friction is going to be based on those two surfaces. Okay, and we're going to call that the coefficient of friction. Okay, kinetic friction has found to be proportional to the normal force, which means the normal force dictates also how much friction is present. Okay, and I'm going to demonstrate that here in a little bit. But here is the here is the equation for friction. And so this will need to go on your equation sheet. This little guy right here is called the coefficient of friction. And that is a standard value dependent on two surfaces. So I'm going to show you some of those in a second. You don't have to write the little k. That just tells us that we're talking about the kinetic coefficient. But the equation for friction is the same no matter what. Coefficient times the normal force. This is a little micro. It's a Greek letter. Lambda. It's like a U with a little tail on the front. Okay, but it's called the coefficient of friction. And there are lots of coefficient of friction values. They're found like in tables. Like people have researched them and found out what's the coefficient of friction between two wooden objects, or between Teflon and something, or between ice and something. They've found all of these values. And we'll look at that here in a second. Okay? But I want to revisit this idea that friction is proportional to the normal force. Okay, so the first thing I want you to do is I want you to just rest your hand on the table. Just lightly rest your hand on the table. The normal force here is just equal to the gravitational force, right? Your normal force is just equal to gravitational because your hand's not accelerating and you're not pushing or pulling, right? You're just resting. So slide your hand on the table. Difficult, try to slide it forward. Difficult, not difficult. Right? Not all that difficult. So now I want you to increase the normal force by pushing down. Now try to slide your hand. Right? What happened? The amount of friction did what? The amount of friction increased, right? As I basically smush those two surfaces together, those surfaces will interact more and more and more. We've increased our normal force, and so the amount of friction has also increased. So I want you to remember that demonstration as we talk about how the normal force affects friction. Okay, second type of friction is called static friction. It's the friction of an object when it is at rest. Okay, and more so I want you to think about this is the amount of friction an object has to overcome to get started. That's really kind of the way you should think about it is. Static friction is how much I have to overcome to get my object in motion. Okay, your book lists another equation for this frictional force, for static friction, but I don't like it. So I put it on the slides, but I'm not going to have you write it down because the frictional force is always coefficient times the normal. But here's the equation that it gives you. It says the maximum friction is the static coefficient times the normal force. That doesn't change the way we solve it. So I really don't want you to write that down because I don't want it to confuse you. We'll always use the frictional force. Frictional force equals coefficient times the normal, right? It means the exact same thing as that. It's just saying the maximum amount of friction you would have is to get it started, right? Once you get it started, it usually can move pretty smoothly. But getting an object started in motion is all about Newton's first law, and it has to overcome a certain amount of friction to go. So, which value should be higher between the two objects, the coefficient of static friction or the coefficient of kinetic friction? Static, right? Think about, is it harder to get an object going or to keep it in motion? It's harder to get an object going, right? That's Newton's first law. An object at rest wants to stay at rest. So in order for me to get it going, I've got to overcome static friction. And then as I start moving my object, or I continue moving my object, I'm overcoming kinetic friction. So I want you to open up your textbook to page 138 and look at these values for static and kinetic friction. So on page 138, that table 2 in the bottom left says their coefficient of friction approximate values. So these coefficient of frictions have been studied and cataloged in these tables. And this is just a small sample of these. But you'll see steel on steel has two different coefficients of friction. One when it is at rest, when it's our static friction, and one when it's our in motion. Okay? What values there have the highest coefficient of friction? Okay, I'm talking about which materials in particular. Rubber on dry concrete. Okay. Why do you think that's good for us? So we can drive, right? It would not be good for us if rubber on dry concrete had a really low coefficient of friction, because what would happen? We would slide. We would slide everywhere. What happens to us in the winter time? What happens to the roads in the winter time? We get ice on the road. Let's see. Rubber on wet concrete has like half the coefficient of friction, right? That's why it becomes so much more dangerous. Ice on ice has 1/10 of the coefficient of friction of rubber on dry concrete. So you see, when you drive on icy roads, your friction amount has decreased by 90%, right? You're 90% more likely to slide, right? Maybe not full 90%, but do you understand what I'm saying? Your friction amount has been reduced by 90%. Yeah.
The static, or the coefficient for static friction is always larger than...
Always larger, good. And there's another theme that encompasses all of them. What seems to be in common with all of those?
They don't go higher than 1.
Very good. No coefficients of friction are higher than 1. So if you're solving and you get a coefficient of friction of 5, right, that's a red flag. Okay, sometimes I make up problems and they come out at a little higher than 1. But for the most part, coefficients of friction should be less than 1. Okay, that's important to remember. So when you're solving and you get a coefficient of friction of 35, no good, right? Take a step back, do something different. All right, the last thing I want to tell you is that the coefficient of friction has no unit. No unit, because if I'm setting up my equation, which is force of friction equals coefficient times the normal force, this is measured in newtons. Here's my coefficient. This is measured in newtons. So when I solve for the coefficient, I divide by newtons, that gives me nothing. Right? I've gotten rid of my units. When I do a dimensional analysis for that, my units go away. So the coefficient of friction has no unit. You don't have to include a unit on the end. It's not measured in newtons. Okay, let's go ahead and try one here. A sled with a mass of 50 kilograms is pulled horizontally along a flat snow-covered surface with a force of 75 newtons. The coefficient of kinetic friction is 0.01. Our overall goal here is to find the horizontal acceleration. Overall goal is to find horizontal acceleration. I'm going to walk that back a little bit and just write that up here because I need some room to write. So go ahead and write down what you need, and then we'll get started with it. right, so let's start with a diagram. I've got gravity. Do I have a normal force?
Yes.
Yes. Okay, I've got some applied force here. I'm pulling at 75 newtons. Okay, and I do have friction. Since it gives me a coefficient of friction, I'm going to assume that I have friction. Okay, force of friction. Okay, I'm going to call this like force applied. All right, so when I go set up my net force equation, I would say F net equals, what's my positive force here? Just the name of the force, not the number. What's my positive force? Force what?
Force
Applied, right? Force applied. My negative force is friction. Okay, so now we start substituting. I want you to start doing every problem. Diagram this equation before you put numbers in.
Then why
Okay.
don't we do the equation with the Fn equals? I mean F.
We're going to get there. We're going to have to substitute to get that.
This is a different.
Okay, we're still going to have to solve that right here. Okay, we know that F net is equal to mass times acceleration, right? We're solving for acceleration, so we're going to leave that as an A. We know our force applied is 75. Do we know the value of our frictional force yet?
Yeah. No.
I don't think so. We don't know it yet. We know that frictional force is the coefficient times the normal force. Okay, I'm going to work it back here. The coefficient we know is 0.01. Do we know our normal force yet?
Yeah. Or no.
I don't think so. We don't know it yet. So I'm going to leave it just for right now. So now this should trigger that, like, oh, we need to go back and solve for the normal force. So since my sled is not accelerating vertically, what do we know about the normal force and the gravitational force? They're equal, right? So if I want to solve for the normal force, if I know it's equal to Fg,
Well, then it's just 9.8.
Oh, mass times 9.8.
right, mass times 9.8. And so that means my normal force is 490, I think. Okay? So now I'm going to come back, erase my Fn, and now I can put in 490.
Wait, can we slow down a little bit?
Yep, I'm sorry.
How did you get, why did you multiply by 50?
Okay, Fg is always mass times gravity, right? So in order to find Fg, I took mass 50 times
Yeah.
9.8, okay? And that gives me my normal force. Now I can come down and plug it in to solve for friction. If you feel more comfortable, like solving for the force of friction separately and then plugging it in, that's fine. But I like to just do everything in one kind of step.
The frictional force is equal to
Coefficient times the normal. Frictional force equation is coefficient times the normal force. Okay, that needs to go on your equation sheet if it isn't already. Frictional force equals coefficient times the normal. Yep. Yes, sometimes you'll get the coefficient and sometimes it'll ask you what is the coefficient of friction, and so you'll solve for it. Right, exactly. Yeah, you won't have to memorize coefficients of friction. Okay, so if I take 490 times 0.01, that gives me 4.9. So I take 75 minus that. 70.1 equals 50 times A. So I divide that by 50, and I get an acceleration of 1.402. A 225 kilogram crate is pulled horizontally with a force of 710. If the crate moves at constant velocity, what is the coefficient of friction?
So F net is 0.
F net is 0, right? F net in the horizontal direction is 0. So write down what you need and try to get your diagram drawn. All right, so
wait,
I'm
it'd be, force applied would be 710.
force applied is 710.
Are those like
Yeah. Yeah.
so you just
Right. Right. Okay, I'm going to walk you through more steps than that, but yeah. Right. Okay, so you guys are there, but I'm going to walk through why that's the case. We know that our applied force and our frictional force are equal because it says it's moving at constant velocity. So I'm going to walk through why that is so we can see it one more time. My F net in the x direction is F applied minus force of friction. And the fact that it's at constant velocity means our F net is equal to 0. Okay, so my force applied minus my force of friction has to equal 0. Okay, so a lot of you were there already. That's fine. I want to just make sure everybody's on the same page. So my 710 minus force of friction equals 0, which means my frictional force has to also equal 710. Okay, does that make sense why that is? Right, constant velocity, you should automatically be able to just say, yeah, those are congruent, but I wanted everyone to see the math behind why that is true. Okay, we don't want the frictional force, we want the coefficient of friction. Right, so if we take force of friction equals coefficient times the normal, I know my force of friction is 710. I'm solving for the coefficient, but we need the normal force. Okay. Okay, we need the normal force. In this problem is our vertical, do we have any vertical acceleration? No. And we only got 2 vertical forces, which means my normal force in this case has to be equal to my gravitational force.
I have a question.
Uh-huh.
So the F applied minus frictional force, can you do like frictional force minus F?
No, we always do positive forces minus negative forces. And positives go to the right, negatives go to the left. Yep, so it's always positives minus negatives. Okay, so that means to solve for Fn, if I know the normal force equals the gravitational force, I take mass times 9.8 would equal my normal force.
2,205.
Okay, 2205 newtons. Then I can come plug that in for my normal force. Okay, then to solve for my coefficient, which way would I divide?
You divide by 2.
Right, I'm going to take 710 divided by 2205. So I should get a number less than 1, I hope. All right. Obviously, right now I'm looking like that's going to happen. Brody, what was your question? One more time?
I figured it out.
I'm sorry, okay.
So this letter should be the one that's less than 1.
Right, the coefficient should usually come out less than 1. No units, so we leave it blank. All right, is everybody's diagram looking something like that? Okay. So it does not matter which one we do first, but since we know we're going to need the normal force, I'm going to go ahead and solve for that first, right? Does that make sense? Why are we going to need the normal force?
To solve
Right. To go into our friction equation, we have to have the normal force. So I'm going to go ahead and solve that first. That way I don't have to go like back and forth, okay? So the first thing I'm going to do is solve things in the y direction. I want to solve for the normal force. Okay, so how many vertical forces do I have?
1, 2, 3.
1, 2, 3. I have 3 vertical forces. Okay, 3 vertical forces. And so when I set my net force equation in the vertical direction, F net in the y direction would be, what force is going upward?
FM.
Normal. What other force is going upward?
Force applied.
Yep, FAPI. And what force is going downward?
Gravity.
Yeah, good. Okay, do we see where those came from? Okay. Now I can start going to put numbers in. What do I know my net force is in the vertical direction? Is my object accelerating vertically? No, because it says it begins to slide. So my net force in the y direction is 0. Normal force is what I'm solving for. Okay, I don't have F applied y solved yet, but I can solve it. Okay, some of you might already have it solved, but I would take 100 times sine
64.
of 40. Okay, thank you. I'm going to go to 64.3. And then Fg is always mass times 9.8.
294.
Thank you.
How do we know I know we should know this, but
It's okay.
how do we know to use cosine or sine?
Okay, if I'm looking for F applied y, it is opposite of that angle, and I have hypotenuse. So opposite and hypotenuse is sine, right? And then cosine is adjacent and hypotenuse. In these problems, when it's set up like this, this will always be sine, x will always be cosine. Okay, so that means my normal force is equal to 229.7. Is that what we got? Normal 229.7. Anyone with questions about how we solved for that?
Shouldn't it be negative?
No, when we do the subtraction here, 64.3 minus 2, that'll give us a negative. Then we have to add it to the other side to make it equal to Fn.
Okay.
Right? And if we have a negative normal force, that means that it's left the table. Right? It's not on the surface anymore, so we can't have a negative normal force.
We're trying to find the acceleration.
We're trying to find horizontal acceleration. Okay? So now I go look in the x direction. My F net in the x direction. How many horizontal forces do I have?
3.
2.
Just 2.
Yes.
Right, just 2. Is this 100 ever going to go into a problem anywhere? No. Right. Just use it to find applied x, right? So my forward force would be F applied x. My negative force is friction. Now I start plugging in numbers. I'm solving for acceleration, so we know our acceleration is not 0, which means I'm going to take mass times acceleration. F applied x is 100 times cosine of 40.
76.6.
Okay, thank you, 76.6. Frictional force is, how do we find the frictional force? Coefficient times the normal, so 0.3 times 229.7. Okay, do we see how those numbers fall into place? All right, that's why we do that prep work ahead of time. That way it's ready to go. And then we just solve. It's very, very similar to the one we just did.
Wait, when we find the frictional force, do we have a unit? So we do put it out.
Right.